Chapter 7, Fluid Power Systems, Part 1 of 3. The questions that we're going to answer in this video: what makes fluid power different from other power transmission methods? What does a hydrostatic force amplify in and output force? What is Bernoulli's principle? How is atmospheric pressure different from gauge pressure and absolute pressure? Basic principles of fluid power. The fundamental concepts that are common to all closed fluid power systems include area, force, and pressure. Area is a measure of the two-dimensional space that is enclosed by a shape. The first step in calculating the volume of a cylinder is to calculate its circular cross-sectional area. The area of a circle is found using the formula pi r squared. Force, F, is a push or pull that acts on an object, causing that object to move, change its motion, or deform in some way. Pressure, P, is a type of load that occurs when a force is distributed across an area and acts perpendicular to the surface. Pressure is mathematically defined as the force per unit area. The metric unit of pressure is the Pascal, which is equivalent to 1 Newton per square meter. Pressure is often measured in kilopascals or megapascals. Pressure is equal to the force divided by the area. Hydraulic versus pneumatic systems. How does an engineer determine if a hydraulic system is more appropriate to use than a pneumatic system and vice versa? The most common deciding factor is based on the compressibility of gases versus the relatively incompressible nature of liquids. Hydraulic systems are more appropriate for systems that require precise positioning of objects. Hydraulic systems are able to generate tremendous power, which allows work to be done on exceptionally heavy loads. Hydraulic systems are also used in situations that call for fluid movements because the output motion of a hydraulic actuator is much smoother than that of a pneumatic actuator. If an application calls for quick movement of relatively light objects across short distances, then a pneumatic actuator may be the most appropriate choice. Compressed air is not returned to a holding tank, but it is exhausted back into the atmosphere. Pneumatic systems operate at much lower pressure levels than hydraulic systems. Neither system is without its disadvantages. Hydraulic systems can generate extremely high pressures, which cause a hydraulic fluid to lose its viscosity. Viscosity is the resistance to flow. If a fluid temperature is not taken into consideration, then the system could develop leaks. Hydraulic systems incur higher maintenance costs than pneumatic systems. Many hydraulic oils are petroleum-based and inappropriate for use in environments that must remain clean. Petroleum-based oils will ignite if exposed to an open flame or extremely hot surfaces. Pneumatic systems have their unique drawbacks. The compressibility makes pneumatic actuators inappropriate for situations that require precise, intermittent motion. The noise that is generated by the compressed gases as they are exhausted to the atmosphere can be significant. An air compressor will use a large amount of energy when generating and maintaining a supply of compressed air at constant pressure. This presents significant operating costs. The internal workings of pneumatic components must be lubricated to prevent seizure. Water will build up in a pneumatic system as a result of the compression process. Water has to be removed on a regular basis to prevent corrosion of the metal parts within the system. Common fluid power system components and schematic symbols. As with every other engineering discipline, professional engineering organizations such as the National Fluid Power Association, or the NFPA, are responsible for developing and maintaining standards that are associated with the design and representation of pneumatic and hydraulic systems. A standard is a reference that is developed by an authority or through general consent and is used as a basis for comparison and verification. Schematic symbols are a simplified graphic representation of an electrical, mechanical, or a fluid power component. They are simple to draw, two-dimensional graphics, for each of the fluid power components found in hydraulic and pneumatic systems. Both pneumatic and hydraulic systems will have a device to pressurize the fluid, a pathway through which the fluid can flow, a device to control pressure, flow rate, and the direction that a fluid will flow, and a device that serves as the point of application. Components include transmission lines, filters, actuators, and directional control valves. The major difference between these components exists in their connections and their design considerations that account for variations in operating fluid pressures. A working line represents fluid transport to and from an actuator or any other device that performs work in a fluid power system. A pilot line represents fluid pressure transmission for the purpose of controlling a valve, such as an air-piloted directional control valve in a pneumatic system, or a pressure relief valve in a hydraulic system. Both pneumatic and hydraulic systems use special filters to remove particulate matter that can damage the inner workings of moving components with a fluid power circuit. Contaminants include dirt and small pieces of metal that are released into the fluid as a result of normal wear between moving parts. Fluid power systems use actuators to convert fluid pressure into mechanical motion for the purpose of moving a load. Single-acting cylinders allows for control of a piston in one direction only. Inside the cylinder is a spring that moves the piston back to its non-actuated position once the fluid pressure is removed. Double-acting cylinders are the most common linear actuators found on heavy construction equipment because they allow for control of a piston in both directions. The pressurized fluid pushes the piston in one direction. The fluid on the other side of the piston is exhausted to the tank or atmosphere. All fluid power systems incorporate one or more types of control valves. The shutoff valve is used to turn all or part of a fluid power system on or off. A check valve is a type of one-way valve that allows fluid to flow in one direction only. This type of valve is often incorporated into other types of valve controls. A shuttle valve combines the functions of a T-connector and a check valve. It has two inlet ports and one outlet port. Inside the valve is a movable obstruction that shifts to close off one inlet port when the other inlet port experiences a higher pressure. A flow control valve is used in both pneumatic and hydraulic circuits to control the volume of fluid as it flows in one direction only. This type of valve is useful for controlling the speed of a piston as it travels either in or out of a cylinder, because flow control valve can only control a cylinder's piston speed in one direction. Hydraulic system components. A reservoir is used in hydraulic systems to store and protect hydraulic oil from outside contamination. The fluid used in a hydraulic circuit will return to the reservoir so it can be recirculated. A hydraulic pump is a mechanical device used to generate the hydrostatic pressure that is transmitted to the actuators in a hydraulic circuit. A fixed displacement system provides a constant pressure and is the least expensive type because of its simple construction. A variable displacement pump allows the user to increase or decrease the pressure that the pump generates. The ability to control the pressures makes this type of pump more expensive than a fixed displacement type. All hydraulic pumps are powered by some type of prime mover, such as an electric motor or internal combustion engine. A pressure relief valve is a type of safety mechanism that is required in even the simplest hydraulic circuits because it will protect the pump and other components from damage caused by excess pressure. A pilot line allows the fluid in the circuit to push against a ball. If an excess amount of pressure is encountered, the ball will compress against the spring and divert the fluid to the reservoir. When the fluid level returns to a safe level, the valve will close again. Schematic symbols for directional control valves are represented by two or more boxes. Each box indicates a position that the valve may occupy during the operation and contains symbols that show how or if a fluid is able to move through the valve from one port to another. The fluid lines in a schematic diagram that connect to the ports on a DVC symbol that represent the valve's neutral position. A four-way DVC has four ports, P, T, A, and B, through which the hydraulic fluid is channeled. Port P is connected to a hydraulic line that provides the pressure. This line is connected directly or indirectly to the pump. The T port is connected to the return line, which sends the hydraulic fluid back to the tank. Ports A and B are the working ports, which are connected to the inlets of a bidirectional actuator. Pneumatic system components. The air that is used in a pneumatic system must pass through a series of conditioning devices before it can be put to use. This process begins when air is drawn into a compressor. The resulting compressed air is then filtered to remove particulates and moisture from the form of water vapor. It then passes through a device that regulates the air pressure to a safe operating level. Oil is then added to the compressed air via a lubricator. Pneumatic pressure is generated by an air compressor. An air compressor does not provide its own power and must be connected to a prime mover. A pneumatic pressure regulator is used to manually adjust and control the pressure of the compressed air source in a pneumatic system. Pneumatic components that contain moving parts must be lubricated to provide continuous smooth operation. The lubricator is usually placed in a series with the filter and the pressure regulator. It uses the pressure from the compressed air to aspirate tiny drops of oil into a fine mist, which mixes with the air and travels throughout the circuit. A receiver tank acts as a holding device for compressed air before it is drawn into a pneumatic circuit. One of the simplest pneumatic DVCs is the 3-port two-way valve, sometimes called a 3-2 valve, which acts like an on-off switch. A solenoid is an electromechanical actuation device that uses the principles of electromagnetism to control the spool within a DCV. This ends part 1.